All right, in this video, we're going to talk about scientific notation. And how we use it in our class. This is not the way a number always has to be expressed, but sometimes a number will be in scientific notation and you'll have to work with it. Or sometimes a question will ask that the answer be put into scientific notation, so you got to know how to interpret it. All right, so what scientific notation is? It's a way to write a really large or really small number conveniently. So it's a way to write a large or small number conveniently. It actually goes along with significant figures, which I'm not going to talk about in this class too much, but in significant figures, everything that's written in scientific notation is significant. So that's another reason it's useful. So I'll just write that down because I know some of you will take AP Chem or college chemistry, and I want to mention it. So it's useful for sig figs. Anyways, so I'll just write chemistry here. And maybe we'll come back and talk about that at some point. And so we get these numbers written in scientific notation that we need to be able to interpret. So what is scientific notation? Well, it is a number between 1 and 10 multiplied by 10 to some exponent. So I think maybe now that we have a definition, a couple examples will help explain that a little bit better. So let's see here. So if we have, say, the number 1, the number 10, the number 100, and the number 1000. All right. And if I put these into scientific notation, we can say that this is equal to 1 times 10 to the 0 power. Anything raised to the 0 power is just 1. So 10 to the 0 is 1. 1 times 1 is 1. For 10, it's going to be 1 times 10, right? But we're going to call that 10 to the first because 10 to the first is just 10. For 100, it's going to be 1 times 10 to the second. So 10 to the second means 10 times 10, so this is 1 times 100, which is equal to 100. And so you get the idea. So here this would just be 1 times 10 to the third power. So if you notice here that we're dealing with positive exponents, right? So when we write this in scientific notation with a exponent of 1, 2, or 3 that's positive, that we get a larger number, right? So I can write that down right there. When the exponent is positive, the number is larger. So what I'm trying to say there is something like this, right? If you were to just look at these three, that when, let me get a different color pen here. When this is a positive 1 or a positive 2 or a positive 3, that these all represent larger numbers than 1, right? because this actually represents 10, this actually represents 100, this actually represents 1,000. So we're going to notice that the opposite is true when it's a negative number. So for instance, then, if I was going to write these down here as 1 times 10 to the negative first, 1 times 10 to the negative second, and 1 times 10 to the negative third, that these would be equal to, this would be equal to 0.1, this would be equal to 0.01, and this would be equal to 0.001. And you don't have to write that 0 out front, right? So I mean, what I'm trying to say there is this could also be just written to, or equal to 0.1. This could be equal to 0.01. This could also be equal to 0.001. So why even, and here you can see the negative sign right here indicating this smaller number. These are all smaller numbers. This is equal to 1/10, right? This is equal to 1/100th. And this is equal to 1,000th. All right. And so the reason why these look different is because this 0 just helps you see the decimal point, is the idea. All right, so hopefully that makes sense. Now, none of these numbers are negative, right? Like, you know, I could have just as easily put a negative sign in front of here and had -10 or -100 or -1,000 with a positive exponent, right? So that don't confuse the two, right? Same thing down here. These are all positive numbers, even though they have a negative exponent. The negative exponent just indicates the size. So when the exponent then is negative, the number is actually smaller. So meaning that because of this negative exponent, the number went from 1 to 0.1, right? Because this exponent is negative, instead of 1, it's 0.01. Because this exponent is negative, instead of 1, it's 0.001. When the exponent is negative, I'll just write this does not indicate a negative number. So once again, you could make all of these negative, but you'd put a negative sign out here, a negative sign out here, a negative sign out there. Same with here, negative sign. Well, yeah, in this one, yeah, that's fine. Negative sign here, negative sign here, negative sign here, negative sign here, and so on. And you can make all these numbers negatives, and then that would be okay. So so there you have it. Whoop, I'm going to go ahead and pause it real quick. So I'm going to look at some examples now from your assignment here. And I'm going to do a few of them and then let you do the rest. We'll start here by looking at numbers 1 through 6. This just says 10 to the second, and that's obviously 10 squared or 100. But think about this as being scientific notation here, and we're going to expand it out. There's really a 1 in front of all these. So this is really 1 times 10 to the second, 1 times 10 to the fourth, 1 times 10 to the seventh. I'm not sure why they left the 1 off. It's confusing, but they should have. I shouldn't have done that. All right, so let's go ahead and start with number 3. Number 3 says, trying to keep this, see somewhere I can reference it as we go. It says 10 to the 7th. So we said we're going to write this as 1 times 10 to the 7th. And here you can see based on the model, right? Each one has a model, each section. For section A, we have to then expand it out. So 1 times 10 to the first is 10. So here, 1 times 10 to the 7th. All right, so we should notice that the exponent is positive. And because it's positive, that means that this is actually a much larger number. And we're going to go ahead and the way we do these is we start by to solve these or to expand these out, what we do is we start by writing our decimal point. And right here, our decimal point is right there after the 1. So if there's no decimal point, then that means it's behind the number. So here, I'm just going to rewrite it just to get a little more room. This means I have to move my decimal point 7 times to make this number larger because it's positive. Now I can move this decimal point 2 ways, left or right, and I have to move it a way that makes it larger. So if I move it left, I'm going to get 0.1. That's not making it larger because it's already at 1. So if I move it right, I'm going to get 10, right? So because every time I move it, this valley it creates, there's actually a 0. But I can't just move it once, right? I have to move it 7 times. So this is the first move. Here we go. This is 2, 3, 4, 5, 6, 7. And a lot of times students will say, "Oh, I get it. I just add 7 zeros because check it out, right? 1, 2, 3, 4, 5, 6, and 7." And it just and don't forget to move that decimal point, right? We're going to put it right there because that's where it is, right? It's now right there. I'm going to rewrite this just for clarity. So it looks like this, right? One more. Oh, no. Do I need to draw the decimal point in now at the end? No, you don't, unless you're doing sig figs, but you don't need to worry about it because it's implied, right? It's always at the end of the number if it's not written. So what I'm showing you there is there's 1, 2, 3, 4, 5, 6, 7. I just do these little lines on top and on bottom so I can count. I know these aren't where the commas go. I know that, right? A comma would go there, a comma would go there, and I would get 10 million. But I'm not interested in that. I don't really care about that. What I'm interested in is making sure I have the right number of zeros. So I have 7 zeros, and it's not always going to be that simple that I just add 7 zeros. It worked out in this case, but it doesn't always work out that way. So we are done. This is our final answer, and I can write it. I can write it with the commas if you really want to see that. Some of you might. And no need to put the decimal point on the end, but you can if you want to. And we're good. Could you have also left it just like this? And would I have been happy with that? The answer is yes. I'm not looking for it written perfectly. I'm looking for it you answering the question, which is to expand it out and get it out of scientific notation. So that was the idea there. All right, let's go to question number 4. Number 4 says, it's similar, but we have a negative sign, 10 to the negative second. So we have 1 times 10 to the negative second, which is what that's saying, right? So same thing, same rules apply. I want to expand this out, right? Following the same model as problem 3. So what first thing I'm going to do is draw my decimal point in. It is right there, right? It's after the 1. So I'm going to rewrite it down here just so I can see a little easier. And then this says I have to move my my decimal point 2 times, but to make it smaller, right, because of the negative sign. So the first move, we moved it last time to the right to make it larger. So to make it smaller, I'm going to move it left, right? Because I move it right here, it becomes 0.1, right? And if I move it one more time right there, then it becomes 0.01. So notice I'm putting a 0 in the valley, right, like before. So I moved it 1, 2 times to the left because this is negative, and it becomes 0.01. Notice that this time, even though this was a 2 for an exponent, a negative 2 albeit, but a 2, I did not add 2 zeros, right? And you might say, oh, we just forgot the 0 out front. Whatever, you don't have to write that. That's fine. You can write it 0.01. 0.01 is perfectly fine. So you can't just add zeros and expect it to add zeros based on the number. It won't work. You get it wrong 50% of the time at least, if not more, and you're not really understanding what's going on. So once again, these are both positive numbers, 0.01 and 10 million. If they were negative, they would have a negative sign here as well. So you would have two negative signs. Ooh. And if this was negative, you'd have a negative sign here. All right, so good. Let's go to number 6. See if I can make a little room here. All right, number 6 says 10 to the 0. All right, we said 10 to the 0 is what? Hopefully you remember. You should be saying that 10 to the 0 is 1, so this becomes 1 times 1, which is equal to 1. Remember, anything raised to the 0 power, 3 raised to the 0 equals 1, 100 raised to the 0 equals 1, x raised to the 0 is equal to 1. So there you go, there's something to remember there. Let's see, what do I have next? I wrote down number 8. Let's look at that one. Number 8 says 7 times 10 to the 4th. All right, I'm going to go ahead and rewrite it. Once again, we're expanding this out, so I'm going to go ahead and do the first step, which is draw your decimal point in, which is right there behind the number. Right? If it's already written for us, for instance, if this problem was 7.5, I wouldn't have to draw it in because it would already be there, right? So if it said something like this, 7.89 times 10 to the negative 3rd, it's already there. I wouldn't redraw it right there. That wouldn't make sense. It's right there. But in this case, I didn't have one, so I had to draw it in. Then this exponent is positive, so I'm going to make this is actually a larger number, right? And so now we got to pick, do we move it left or right? Well, if we move it this way, we get 0.7. That's going to make it smaller, so I'm going to go ahead and move it to the right, and I'm going to move it 4 times. So that's going to look like this then. So at 7, I'm going to move this, let's see, 1, 2, 3, 4. And therefore, I'm going to get to add 1, 2, 3, 4, and draw my new decimal point in. So don't leave it in this form because this is confusing, right? Like, was the decimal point here or is it here? And I see students do that sometimes. I don't know if I'm grading this and this is your test. So you have to rewrite it so it makes sense. So it would be 70,000. And if you want to put the comma in, you can. That's fine. There you go. All right, problem number 9. Let's look at next. Number 9 says 900 times 10 to the negative 2nd. All right, I like this one. Yeah, that's fine. 900 times 10 to the negative 2nd. Let me say something about this. A lot of times students on a test will get it wrong because they didn't put their scientific notation to a number between 1 and 10, right? That was our rule here. It's a number between 1 and 10 multiplied by 10 to an exponent between 1 and 10. 900 is not between 1 and 10. Now, even though it's incorrectly written in scientific notation, you'll still see numbers written like this, and we'll still call it scientific notation, but it's not written as well as it could be, is the idea. So since this is physics class and we're learning scientific notation, we will always write our numbers between 1 and 10. So you won't write them like this. But sometimes this will turn up in a homework assignment, or this will turn up in an assignment where you have to deal with this. So we deal with it the same way we did before, which was, what was our first move? Write the decimal point in, right? Okay, I don't see a decimal, so it's got to be after the number, so it's right there. Then this is a negative sign, so this is actually a smaller number. So I'm going to move it a way that makes this smaller. This is 900. Well, if I move it this way, it makes it 90. So I'm going to do that. I'm going to go left, and I'm going to go how many times? Well, 2, right? So 1, 2, right there. And now it's a mess, right? So I'm going to go ahead and rewrite it. So I have 9 as my answer. You could write the point in as if you want. So keep in mind what this is saying and why I can't just leave it like this, right? That 9 is equal to 900 times 10 to the negative 2nd. So these are the same, these are one and the same, right? These are the same thing. This is the same thing as this. Meaning if somebody offered to give you 900 times 10 to the negative 2nd dollars, they would still be just giving you $9. So these two are equal, and that's something to keep in mind. All right, good. Let's go to the next one, which is number 11. And 11, I got some room right here, is, or did I just do 11? I think I just did number 11. Dang it. All right, well, we will just go ahead and call this number 11, and then call this one number 9 over here, and that'll be good. I'm not going to go back and redo that. Number 9 says 2.4 times 10 to the third. All right, so I'm going to write it here, 2.4 times 10 to the third. Once again, we got a positive exponent, and finally our decimal is written for us, so we don't have to rewrite it, right? You wouldn't write it right there. That'd be wrong. So what we do then is we're going to move it 3 times. We're going to make this is actually a larger number. This right here is actually larger than it looks, right? It looks like 2.4, but it's actually larger than that because of this 10 times 10 to the third. So I'm going to move it 3 times in the way that makes it larger, which would be to the right. So 1 time gets me there around the 4, 2 times, 3 times. The 4 is in the valley here. Here there's no number in the valley, so it's going to be a 0. Here there's no number in the valley, so it's going to be a 0, and I'll draw my decimal point. So what that's going to look like then, if I clean it up a little bit, is going to be 2400, right? 00, and then decimal. And so what we're saying is 2400, right? If you want to write your comma in, you can. Just put it right there. Is the same as 2.4 times 10 to the third. Those are equal. All right, good. So here's our answer right there. And good. Let's go ahead and go to number 17. Mm. 17 says 0.3 zeros, then a 1. All right, so 17 says 0.123, then a 1. And this time we have to go to scientific notation. So we have to get it to be a number between 1 and 10, right? So if I move this decimal to the left, I'm just going to end up adding more zeros. So I wouldn't do that, right? To get it to be a number between 1 and 10, I'm going to have to move the decimal this way, all right? If I move it there, it becomes 0.001. That's not good enough. And still not good enough. Still not good enough. Right there. If I put that decimal right there, it becomes 1 point, which is a number between 1 and 10, right? A single digit number. But this doesn't equal 1, right? So I can't just leave it as 1 point. I can't just leave it like that, right? So because this doesn't equal 1, right? That doesn't make sense. So what does this equal? Well, I had to move it 1, 2, 3, 4 times, right? So it equals 1 times 10 to the 4th, but because it's actually a much smaller number, right? Meaning that this is equal to 0.0001, I have to, in order to show these are equal, I have to account for the fact that this 1 is actually much smaller. It's actually this, right? So how do I do that? Well, you should remember, right? Just make this negative. So by adding that negative in the exponent, I am telling the person reading this that this is actually a much smaller number than 1, that it's actually equal to this, right? Because maybe all they see is that, right? And they're like, well, what the heck is that? Is that 1? No, it's a much smaller number. It's that. And so that negative sign has to be there. It's not a negative 0.0001, but it's still positive, but the negative exponent just means it's a smaller number. All right, cool. Number 23. Okay, so 23 is down here. Let's see, 0.0034. All right, so here, we're going to do the same thing, right? To make a number between 1 and 10, we got to write it in scientific notation. So once again, which way am I going to move this? Well, if I move it this way, this just gets smaller and smaller. It becomes 0.000. I wouldn't do that. So I want to get a number between 1 and 10. So I'm going to go this way. 1, 2, 3. Now I could move again, but if I stop here, I have 3.4. Is that between 1 and 10? Yeah. So I'm just going to stop right there, draw the decimal point in. It becomes 3.4. But we're not done, right? We can't leave it as just 3.4 because 0.0034 does not equal 3.4, right? So now I need the times 10 to the, well, it's a much smaller number than 3.4, and I had to move the decimal how many times? 1, 2, 3. So times 10 to the third, but since this is actually, this 3.4 is larger, to account for the fact that it's a smaller number, right? Because these two are equal, you need the negative sign right there. So that shows that this is actually a much smaller number than 3.4. All right, good. Let's go to 25 next. In 25, we're given this kind of difficult to deal with number. All right, so expand this out, right? And first question, is this a smaller or larger number? You should say, well, exponent's positive, so it's much larger. And so that's the way, that means we're going to expand moving this decimal which way? Well, if we move it to here, it becomes 48. If I move it to here, it becomes 0.4. This has to be larger, so I'm going to move it the way that would make this larger, which is to the right. So 1, that's 1 move. 2 moves, 3 moves, 4 moves, 5 moves. I gotta move this 15 times. Dang. All right. So one more time. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And put the decimal there. Then everywhere there's a valley, I'm going to add a 0. So there would be a 0 here. All right, these are all good because they have numbers there. There would be a 0 here, 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 a 0 here. All right, it's a lot of zeros, right? So now let's go ahead and rewrite and clean this up. 4, 8, 7, 0, 8, 9. How many zeros is that? I can't really see that really well because I just don't want to screw it up. Maybe it's a test and I want to make sure I get the question right. So I do this little trick, right, which is the underlining system. I just underline 3 of them, and then I go to the top and underline 3 more. Now I can see that there's 6 zeros right there, and then I'm going to keep doing this. And then now I'm at 9, and I got 1 more, so that's going to be 10. And this just helps me count. So that's the whole point of this, right? It's just helping me count and see that there's 10 zeros. Because sometimes your eyes can deceive you a little bit, or if you just count, you might make a mistake. So I like to draw these little lines over it, and it helps me count. So anyways, I'm going to go ahead and add the 10 zeros. So I'm going to do it in a way that's kind of crazy looking. Check this out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then draw the decimal point. And there's my answer right there. You might say, well, that looks stupid, or that where are the commas, but you don't need that, right? You just needed to expand it out and make sure that you had the right number of zeros. So by writing it in this way that looks stupid, you're able to clearly show that there's 10 zeros here, right? And you're not going to make a mistake writing it when they're all smushed together, right? So it's easier by separating them into little groups is what I did there. And then that way you get the question right. So that's the idea. Now, if you're a stickler and you're like, no, I got to write it with commas, by all means, but start making your commas go this way, right? So 1, 2, 3, comma, 1, 2, 3, comma. I guess you could still put them in. That would look something like this, right? I got an orange marker here. Let's see. 1, 2, 3, there'd be a comma there. 1, 2, 3, a comma there. 1, 2, 3, a comma there. Hopefully you can see that. 1, 2, 3, a comma there. 1, 2, 3, a comma there. And so, what would that be? I don't even know. This would be thousands. millions, billions, trillions, quadrillion. Yeah, so 4.87 quadrillion. Sure. All right. That's why I use scientific notation, because this is obnoxious. All right, let's go ahead and and that's why you would write it like that. So let's go to number 26. And I only got two more here and we'll be done. So 26 says, put this into scientific notation. What is this? This is this crazy looking number. Let me see if I can write it. I can't even see how many zeros that is. It's something crazy. 1, 2. See, and this is, I don't want to ruin this worksheet, so I'm going to have to bring this close to my eye to double check. 2, 3. I think it's 15 zeros. I can't even, normally I would just write it right over the top of it, but I don't want to, like I said, ruin this. I guess I could get a pencil, and let me see if I have a light pencil to write with so I don't ruin this worksheet. 1, 2, 3, 4, 5, 6. This is hard on my eyes. Let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9. 2, 3, 7, 8, 9, 10. Yeah, that's 15 zeros. Boy, that took a long. That was hard for me to see. All right, so I'm gonna rewrite it just so. Okay. All right, I had to pause there for a second. This is 6, 7, 8, 9, right? Yeah. So I'm gonna go ahead and write that in. So what I was trying to say before is that when you're confronted with 15 zeros like this, 16 if you count this one, but I'm not going to, is that you use this system, right, of drawing lines over the top and bottom so that you can count and know how many zeros you're dealing with there. And that's what I would have did on that other sheet, but I didn't want to mark it up too bad, and I used a pencil and ended up doing it anyways. All right, but it doesn't change how scientific notation works, meaning we still got to move this decimal all the way past all these zeros and then one more around the 6 to get 6.789, right? So that's exactly what we're going to do. So I'm going to count it out just for fun here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I had to move it 16 times. So I'm saying that this mess right here is equal to 6.789 times 10 to the 16th. But because this 6.789 is equal to this really tiny number, I have to represent that somewhere here, right? Because this equals this by having this negative sign here. All right, and that's see how much nicer that is to work with than that. I mean, that's just, yeah, that nobody wants to work with that. All right, so finally, number 28. 28 says circle which is bigger, and on 28 we're given a choice, 56,783. Work right at the bottom here. 56,783, or 5.6783 times 10 to the 5th. And so, which do we choose? Well, it's kind of hard to compare when they're not written in when they're either both not in scientific notation or they're both not expanded out. So I think it's easier maybe if we just expand this one out and then compare 56,000 to this. So I'm going to move this. This is a positive here. So this is actually a much larger number. I'm going to move it 5 times to make it larger, which is to the right. 1, 2, 3, 4, 5. Got an empty valley right there and a decimal point right there. So I'm going to go ahead and rewrite it. 5, 6, 7, 8, 3, 0 points. And so you can now see that 567,830 is larger than 56,783. All right, so there's our answer right there. Good. That's it. So you can do the rest of them and let me know if you have any questions. All right, that's it. Take care.